Recording has started.
So for number one, define the perimeter and the area. Well, let's do the perimeter first. The perimeter here is in three pieces. We have a 12-inch radius here. We have another 12-inch radius here. And then we have this arc up here that we have to add to that. So we need to find that arc length. To find that arc length, remember it's the circumference of the whole circle. So that would be pi times 24. Remember, it's pi times diameter. So we have to double that 12-inch radius to get a diameter of 24. That would be the circumference of the whole circle. So then to get the arc, we go times 30 degrees over 360 degrees. Because 360 degrees would be the full circle, we only have 30 out of those 360 degrees. Which I believe gives us 6.28 inches for that arc. So we add that to our 12 and our 12. We get a total here of 30.28 inches for our perimeter. How many of you had that? How many of you would have had that if I gave you more time? How many just want to go home and cry? Not yet. Maybe? Okay. Well, I'm glad we haven't pushed you that far in the first 7 minutes at least. For area, this is a sector. Remember we said that pi wedge shape is called a sector of a circle. It's the area of the full circle. That would be pi times 12 squared. That's the area of the full circle. Again, times 30 out of 360 degrees. Notice I'm not labeling the degrees anymore because the degrees are just going to cancel out anyway, so it doesn't really matter. So we have pi, I'll do 3.14 times 12 squared times 30 divided by 360. 37.68 we get there. That is our area. Of course, the lengths are in inches, so that area will be in square inches. Not so bad. You guys need a little bit more time to work on number two? Yeah? Okay, I'll give you another minute or two, and then we'll go over number two. So to do the perimeter, we'll pick a spot and we'll just travel around the shape, adding up the lengths as we go. So here, that length is 12 millimeters. I'm just going to put 12 to save some space here. This distance across here, well, it's not labeled, but we know that if this is 8, this has to be 8. And of course, if that's a sector of a circle, that would have to be 8 because they're both radii of that circle, which makes this also 8 millimeters. This would also have to be 12. This has to be 20 to match the other side. That side is 8, and this side is 20. And once again, we need to add the arc of that circle here. This arc here. The hard part is, well, what degrees is it? What's it measure? Well, we know that being a rectangle, this is a square corner, or 90 degrees. This is also a square corner, or 90 degrees. 90, 90, and 140 add up to 320 total degrees from here to here, which means this has to be 40 degrees because a complete circle is 360. So we can use that to find that arc length. The full circle would be pi times 16. Remember, radius of 8 makes it a diameter of 16. Times that 40 degrees over 360. So we will do 3.14 times 16 times 40 over 360. Giving us 5.58 millimeters for that arc. So that's all of our pieces there. What do we have? We have 20, 40, 60, 85.58 millimeters for our perimeter. Did anybody get that far, or did you need more time? Not quite, cut you short? Okay. For this one, I believe the area is almost easier to do than the perimeter. We have 3 shapes. Shape number 1 is a rectangle that's 12 millimeters by 8 millimeters. That's 96 millimeters squared. Shape 2 up there is also a rectangle that is 20 millimeters by 8 millimeters, or 160 millimeters squared. Shape 3 is that sector of a circle. So to find that sector area, it's going to be the area of the whole circle, pi times 8 squared, times, again, that 40-degree central angle out of 360 for a full circle. 3.14 times 8 squared times 40 over 360. Now you might notice I've left my zeros off. 40 over 360 is the same as 4 over 36. It just saves me a couple keystrokes is all, but it's the same calculation. So at 22.33. That is millimeters squared. So we add that all up, we have 96, 256, 278.33 millimeters squared for area. Excuse me. So these problems can get, excuse me, there it was. Pardon me. These problems can get more and more complex as we go. And as you've seen, probably the biggest thing is time, having the time to break them down and finding the different pieces. And of course, I didn't give you nearly enough time on either of those problems. Looking at them, does anybody have questions on why I did what I did with any of those? So let's look at one that's maybe a little bit unique. So I will tell you that that is a quarter circle there. We got 10 inches here and 15 inches there. That's going to be 5 inches. This is going to be 16 inches. And I will tell you that those pieces line up. So I want you to try to find, once again, perimeter and area for that shape. Obviously, I'm going to have to give you more than a few minutes for this one. So we'll give you about 4 or 5 minutes, and then we'll go over that one. See what you can come up with.
You got a red dotted line that goes from the 10 to the 5. Do you want us to find the area inside that square there too?
Nope, that dotted line is just telling you that those two pieces line up. Is all that's saying.
Oh, okay.
Yeah, so you can assume it's flat across here, and it is flat across the bottom down here. How are we doing? Are we ready or do you need another minute? Take a look at it. Okay, so this one is a little complex. Let's do for perimeter. Let's start right here and we'll go around. This piece, we need to find that length. Well, if that is 5 inches across here, that means it's 5 inches here. So that has a radius of 5 on that half circle. So that radius goes in both directions. That would make this 5 inches. Same over here. If this is 10 inches, that makes this 10 inches. And this 10 inches. So that means we have an overall height here of 15 plus 10 or 25 inches. We have to have the same overall height over here, which means that being 5, this is only 20 inches here. So for our perimeter, we start out, we've got 20 inches there. We got 5 across here. Another 20 going down here. We have this arc that we're going to have to come back and fill in. So let's find that right now. That is a circle with a radius of 5, so it'll be pi times 10. That would be a diameter of 10 times 90 over 360. Now, since that was a quarter circle, we could have just divided by 4. What does that give us? 78.5 inches there for that. Oh, something's off there. No, 7.85. I believe, let me double check it. It is 7.85. So we put in the 7.85 inches up here. Then we can continue to go around that 16 inches. Then we have another arc length here. I'll do that one in purple. So that arc length is pi times 20, because that is a radius of 10, so diameter of 20, also times 90 over 360, giving us 15.7 inches for that arc length. Plus, we have 15 there, 10 inches there, another 15 inches here, and finally we have this piece here. That piece is part of a triangle. We know this is 16 inches here, and we know this is 5 inches here. That's the difference between the 10 and the 5. So that arc across there, the hypotenuse, not arc, I should say, that hypotenuse is 5 squared plus 16 squared equals, I'll call it just x for now, x squared. So 5 squared, of course, is 25. 16 squared is 256. 25 plus 256 is 281. So to find that length, we have to square root. Square root of 281 gives us 16.76. So that final slanted, that hypotenuse, is 16.76 inches. So that all adds up to be, what is that, 25, 45, 60, 70, 85, 101. And we have a total of 141.31. Did anybody have that? Or within like a half an inch of that with the round off for using pi? Any questions on how I got that? So as you can see, some of the missing dimensions are kind of tricky to find, but they're there if you dig for them. The area. We have 5 distinct pieces here. 1 and 2. We'll call this one in here 3. And then the quarter circles will be 4 and 5. Area 1 is just a rectangle that's 15 inches by 10 inches. That would be 150 square inches. Area 2 is also a rectangle that is 20 inches by 5 inches, or 100 square inches. 3 is a little bit more complex. Now I could have cut 3 into 2 other pieces. Could have cut it into that 5 by 16 rectangle and then a 5 by 16 right triangle. But I can do it all at once as a trapezoid. The small base, this would be the small base here, is 5. The large base is over here, that's 10. So I average those together and I multiply by my height, which is the 16, the distance between the bases. That is 120 square inches. Piece 4 is a sector of a circle. That's pi times 10 squared times 90 over 360, since it is a quarter circle, or 90 degrees. So I believe that is 78.5 square inches. And piece 5. Pi times 5 squared, gets a radius of 5 there. Either divided by 4 times 90 over 360, either way works. Which is 19.63 approximately square inches. So if I add those up, we say 468.13 square inches of area. Any questions there? Now, one major application of these areas, not necessarily big in machining, but it's big in construction and mechanical systems. It can be big if you get into the hydraulic side of it, dealing with head pressures. I'm more familiar from, rather than the hydraulics, I'm more familiar from the heating and cooling side, the mechanical side of it. Dealing with ductwork. Like I said, the exact same principle applies to hydraulics as far as, branching off and maintaining pressures and lines. It's the exact same concept. So let's say we're going to start out with a 12-inch by 14, let's go 12-inch by 18-inch main duct. Now, if you're familiar with ductwork is the piping in your floor or ceiling that runs heat and air conditioning through a house. So we have a certain area here that air is going to flow through, that full area. So that area is 12 inches by 18 inches, or 216 square inches. As we go through the system, we want to slowly shrink it as we branch off so that the total area leaving a juncture is equal to or maybe slightly less than the area going in. We don't want it to be too much less because then you increase your air velocity, but you do want to have a pressurized heating system. So this duct might go down the line where it branches off with two 6-inch diameter round ducts branching off of it. So let's find the area of those 6-inch diameter round ducts. The area is going to be pi times not 6 squared, but 3 squared. Giving us 28.26 square inches for each of those. So we have lost here 28.26 times 2, 56.52 square inches of air branching out. So that means we have to shrink the main duct here. This duct gets smaller so that it restricts the airflow. Basically what happens is if air is flowing here, if this duct gets smaller like it is, it forces some of the air to go out these other ducts. It's called back pressure in a system. So we need to reduce the area by 56.52 square inches. So my previous area of 216, let's minus 56.52, gives us 149.48 square inches. So we might reduce this down to get to about that area. We might reduce this duct now down to 15-inch by 10-inch, which would be 150 square inches, almost exactly what we need. And so as you go through the system, you need that reduction each time you branch off. Let's say we go down through here more and we branch off again. This time, let's say we're going to branch off 3 6-inch ducts. So the total area that we've lost is 3 times this 26.26 or 28.26, which is going to be 84.78 square inches. So we have to subtract that off of our remaining area. So we subtract here, we've got square inches. 0.746 64.76 square inches left is what we need. About 65 square inches, in other words. So we might reduce that down here to a 5 by 13. So you can see what happens as we go down through there. And at this point, we've only got room to branch off 2, maybe 3 more ducts from that main duct before we've lost our back pressure. The same concept applies in the other direction for water flow in a house drain. You have to prepare a house drain to handle full flow from all inlets. So let's say we have a 2-inch drain coming from a shower. Let's say we've got a 1.5-inch drain coming from a sink. And we'll go with another 1.5-inch drain coming from another sink. And these are all coming in together here to juncture. What size pipe do we need coming out of that juncture in order to handle that flow? So our area here is pi times 1 squared. Remember, a diameter of 2 gives us a radius of 1. That's 3.14 square inches. This is going to be pi times 3/4 of an inch, or 0.75 squared, half of the 1.5. 3.14 times 0.75 squared is 1.77. And of course, we have 1.77 square inches here. So we add all those together to get a total here. What, 14, 18, 16, 6.68 square inches. So that means that we need this pipe here to be big enough to handle 6.68 square inches of flow. So now we have to work backwards to find what the diameter of that pipe has to be. So when we find area, we square the radius, and then we multiply by pi, so times 3.14. Working backwards, we got to go the opposite. We're going to divide by pi. So 6.68 divided by pi, divided by 3.14, gives us 2.13 about. And then we square root that. So second square root, remember we have that button on our calculator, we can tell it to use the previous answer. We get 1.446, I guess we'll call it, inches. That's radius, so the diameter has to be twice that, which comes out to be 2.92 inches of diameter. So this needs to be a 3-inch pipe here, 3-inch diameter pipe, to handle the inflow from all three outlets if it comes in at full flow. Now, in the actual plumbing industry, there's a percentage that you have to run a full flow. You don't have to assume that every inlet is coming at full flow, but you do have to be able to handle, I believe it's 70% of full flow at each juncture. Okay, well, it is 8:15 right now. Normally, I'd give you a little bit of homework and let you work for a little while before we take our break. But let's take our break a few minutes early today. We'll come back and we'll resume lecture at 8:26. It's almost 8:16. So just take 10 minutes, we'll come back, and then we'll talk about octagons when you come back.
Where is, I cannot find M8.
The beginning of birds.
Or access. X, Y, and Z.
Oh my god. Let's
So-
just say, because Richard's like, you don't need no to that.
No, and Thomas has actually a 7-axis mill.
Oh, yeah. Didn't
They
you
do a
ever
lot.
tell Alex? That doesn't make sense. That doesn't make sense.
Yeah, they don't. He's like, well, he's never asked them. Yeah, he said that C pretty much just like rotates when they do loggers
Oh my gosh.
for some of the big big ups up in there for
Oh yeah.
it's gotta be turned at a certain
I didn't
He's got-
even know half these places existed.
and he's got live tuning. Just live tune on the drip, so it's
I didn't find thread per inch.
threads per inch for one big. That's how many.
Oh, it's
So be
just 20.
20 times. That's one times 1 inch. That's
Oh.
20 threads.
What?
Or 1 divided by 20. Okay.
What's the black?
It's gonna be a point. So. Yep.
And 8. Supposed to be 10. So, 1.5. I'm just doing it.
That's what I did because I think this is there.
I'm gonna cross it out. Then he'll know what I did.
Yeah, it goes M8 by 1.25.
Yeah, like,
Or it goes M8 by 1.
yeah, 1.5 is more.
Like
I don't even know if I did that worksheet right.
half 20 UNC that
The pitch. This, did you just
pitch.
add them both and then divide by 2? Like the pitch diameter?
It's possible. I didn't actually do that. That's what I did.
Oh god, no.
I think you did. Whatever that number is.
Oh well. Because again, every time you fail this section.
I will tell you that when you get to there, take the number in the book times 25, 24. Because that's all answers have decimal inches.
Oh, yeah, I was wondering about that. So all these must be
Or divided by. Yeah, because it's smaller. It should be roughly around that.
These ones, I seriously just took these two numbers, added them, and divided by 2. Or wait, I took these two.
I mean, my brother actually deals with a lot of this stuff.
Yeah, 0.2.
Zero, one, two.
What the? Oh well.
I trust my brother because he actually
Yeah, I know.
he does this. He does the threads all. But he does.
Well, he didn't really explain to us. So
I
like,
used to look it up.
if I get them wrong, I get them wrong. That's what I meant.
Actually, there's 16. Grab that thread. Those things. How many threads do you make cut per
It's
inch?
how many threads are in one. What thread depth? What
It's
is
actually
it?
not in the book. You gotta look at the roster. Actually,
Is it one you have to turn one way, not into?
left hand thread.
Yeah, I know.
Standard thread and 80%.
No. 75,
Yeah, it's our, you know, you go on.
Oh, yeah.
You
The
know,
last one's 7.
what?
No.
It's,
Oh, take it. I was thinking
it's
Well, I'll do
3/4,
that.
so 3/4. Oh, and this, there's nothing in the book that says Acme threads. Well, my brother said he works with this every day. It says bigger parts with bigger. Four axis. I don't think he always uses it, but most of the time. Because sometimes he's running like really big certain parts.
that must make good money there. Yeah.
Where? Thomas Precision. And they have a 7-axis mill there too. And I think a 5.
I'm telling you, Richard thinks none of that exists.
Yesterday he told us that no one in this area has more than a 3-axis mill. Then I had to ask my brother for some help with this homework that he gave us. He goes, he's lying. We have a 4-axis lathe that he runs, and a 5 and 7-axis mill. There.
What would happen if you were to quit?
I think at Parker,
Yeah.
We would go this.
I think at Parker, the most we've got is a couple 4-axis Akumas.
Yeah.
Maybe our Nakamura
Are they mills or lathes?
lathes.
The hard part around here is finding anybody that's trained or capable of training somebody on anything more than a 4-axis machine. There's not many people in the area that know how to run anything more complicated than that. They've tried to set up training programs at CVTC for it, for the 5 and 6-axis stuff, and they have struggled to find students that are willing to do it, and then the people that are trained to do it or that are knowledgeable enough to train how to do it can make a lot more money in industry actually doing it. Well, let's go ahead and pick up here. It's that time. So our topic here for the last section of the class here, we want to talk about finding the area of octagons. But not just any octagon, we're going to look at a regular octagon. By regular octagon, what we mean is that it's all sides are the same. All the sides are equal, all the angles are equal. So on a regular octagon, as far as measuring lengths for dimensions, there are 3 dimensions that we can measure. One is the length of the side. I'm just going to call that S. Another that we can measure is called the flat dimension from one side to the opposite side, which we'll label F as our flat dimension. And the final one goes diagonally from one corner to the other. We're going to label that D for diagonal. Now these dimensions are chosen because they have meaning outside of the octagon, meaning in machining, to be honest. If I were to cut this octagonal piece out of a round piece of round stock, so let's say I don't have that octagonal stock, I need to take a piece of round stock, machine sides flat to make it. The smallest round stock that I would require would look like that. It would have a diameter of D. That would be the diameter of that smallest round stock. Now, if for some reason we had octagonal stock and we're going to turn it down to make a round piece out of it, or at least part of it is going to be round, the largest round piece we could get out of it would be inside here like this. The diameter of that largest round piece would be F, that flat distance. So these dimensions do have meaning outside of the octagon. What we want to start off with is finding the area from these dimensions. So let's find the area if we know the side, length S. So if we know length S, the area of that octagon is 4.8275 times S squared. Well, what's that mean? Well, let's say we have our little octagon there. Then that octagon has a dimension on each side of 8 millimeters. The area of our octagon is then 4.8275 times 8 squared. Give us 308.96 millimeters squared. Why would we ever need to do this calculation? Well, you get into stress and strain characteristics of material when it's going to be working under a load. It has to be able to support a certain amount of force. You have to know what's called the cross-sectional area of that piece. If this is a piece of octagonal stock, one of the dimensions that's going to be real easy to measure on it is the length of that side. If you measure the length of the side, you can find the total cross-sectional area of it So you can then calculate what is its maximum load that it can carry in a stressed situation, in a loaded situation. Well, let's say that we know the flat distance, F. Well, in that case, then the area of our octagon is 0.8284 times F squared. So, pretend my drawings don't suck and these actually look like octagons. Flat distance would be side to side like that. Put a caliper on it on the flat sides, that would be the dimension you would get. Let's say we have a piece of stock here that is 3/4 of an inch. So then that area would be 0.8284 times 0.75 squared. .8284 times 0.75 squared gives us, 0.466, it looks like, about square inches. Once again, if we were looking at this under load, if we didn't have the specs on that octagonal stock that told us the length of the side of the octagon, if we're trying to measure it, measuring the length of that side, trying to put a caliper or something on to measure from here to here is tricky to do. We can slap a caliper on it and go side to side like that and get that flat measurement, that measurement F, and find that area for calculating that stress. Finally, what if we know D, the diagonal? Well, then the area is 0.7071 times that diagonal length squared. So the diagonal length, of course, is going to go diagonally across here. Let's say that we know that is, well, let's go with 18 millimeters. So then the area of this piece, 0.7071 times 18 squared. Gives us 229.10. Of course, that'll be millimeters squared. So this type of a calculation would be, again, if you're looking at that round piece of stock and you're going to need to trim it down, you need an octagonally shaped shaft for some reason. You're going to trim it down to an octagon, but you still need a minimum cross-sectional area in order to handle the load that it has to be under. This is going to tell you what is that diameter of that round stock, the minimum size of that round stock that we can trim down to make the octagonal shaft that we need. These formulas, by the way, are in your packet. I believe it's page 170. So if you didn't get them all written down, they're in your packet on that page for you. In your notes, I want you to find the area. Of an octagon with a side length of 0.5. I'll give you half a minute or so, then we'll go through that. . So the area for that, since we have the side, is 4.8275 times that side of 0.5 squared. Giving us 1.207 square inches of area. If we have a piece of octagonal stock that has corner to corner length there of, let's call it 1.20 inches. Find the area of that for me, please. So that would be the dimension D. So the area, if we have the dimension D, the diagonal, is 0.7071 times D squared, so times 1.2 inches squared. Giving us 1.018 square inches. Finally, one last example. So for this one, we have a dimension across there of, well, let's go 15 millimeters. Find the area of that. So when we have that flat dimension, the area is 0.8284 times that dimension squared, which gives us 186.39 millimeters squared. So let's take a peek at how this can be applied. Again, I'm going to look at some construction examples just because that's where I have more good examples, but as potential homeowners and stuff, they could be useful to you. Let's look at building an octagon gazebo. A pretty common yard object. And let's say you're building this octagon gazebo, but you need to make sure that the distance across is no more than 16 feet. But you want to know what side length you can have here from that. what's the length of the side going to be if you're restricted at 16 feet? Well, 16 across there, that is the F, the flat dimension. So let's find the area based on that. Now, we could find S in other ways. They would involve using trigonometry. Right now, we don't know trig, so we're going to look at ways of using these formulas to find those dimensions without using trig. So the area based on that flat would be 0.8284 times 16 feet squared. Giving us 135.27 square feet. Now we can work backwards like we did with our circle formula. We know they have 135.27 square feet. We know the area, if we use the side, would be 4.8275 times the length of that side squared. So now we're going to work backwards to find the length of the side. We're going to divide by that 4.8275. So our 135.27 divided by 4.8275 gives us 28.02. Well, that's the length of our side squared, so we still have to square root it. Second square root of that previous answer gives us 5.29 feet. So the maximum length of that side is 5.29 feet, or about 5 1/4 feet. Well, let's go back to looking at that round stock. Let's say you go into this supply rack or whatever, you need to create an octagon shaft. And what you have in there is round stock that has a diameter of 20 millimeters. You want to know what is the largest as far as the length of the sides. What is the largest octagonal shaft you can create from that? Well, what we have here, 20 would be D, the diagonal. So if D equals 20 millimeters, the area of that is going to be 0.7071 times D squared. Times 20 squared gives us 282.84 millimeters squared is the area of the shaft we could create. To get back to that length of side, we know our area, and we know for the length of the side it's 4.8275 times the length of that side squared. So once again, we're going to work backwards. We're going to divide by the 4.8275. Get 58.59. That is the side squared, so we have to square root that yet. Square root of that previous answer. 7.654 millimeters would be the length of the side. Of the largest octagon shaft we could cut out of that. Make sense? Okay, so since I didn't give you any work time in the first hour, I'm going to give you extra work time here. Partly because that's just a good natural break in the material right here. So we are going to look at, in that packet, There's page 170, that gray box on the octagons. Then there's page 174 through 177, which is perimeters and areas of those composite shapes, like what we were doing at the beginning of the class this morning. So we do have about 30 minutes left. If you want to hang around and work on homework, I'll stay on the network to answer any questions. Otherwise, that is all of our material for today. So if you would like, you are